Imagine standing on a mountaintop on a clear night, gazing up at the countless stars scattered across the darkness above. Each pinprick of light has traveled millions, sometimes billions of years to reach your eyes. That light, racing through the emptiness of space at an almost unimaginable speed, represents the fastest thing in our universe. But what if you could move just as fast? What if you possessed the incredible power to travel at the speed of light itself? Light moves at 299,792,458 meters per second through empty space. To put this in perspective, light could circle our entire planet over 7 times in just 1 second. It could travel from the Sun to Earth in about 8 minutes and 20 seconds. This incredible speed has puzzled and fascinated scientists for centuries, leading to some of the most profound discoveries about the nature of reality itself. When we look at the stars, we are actually looking backward in time. The light from the nearest star to our Sun, Proxima Centauri, takes over 4 years to reach us. The light from distant galaxies has been traveling for billions of years before entering our telescopes. In a very real sense, light is a time machine, carrying information from the past into our present moment. But what would happen if you could join that light on its incredible journey? What would it feel like to move at such an extraordinary speed? How would the universe appear to you? Would time itself behave differently? These questions have captivated physicists, philosophers, and dreamers for generations, leading to some of the most revolutionary ideas in modern science. The concept of light-speed travel challenges everything we think we know about space, time, and reality. It forces us to confront the limits of physics and the boundaries of what might be possible. When Albert Einstein first proposed his theories about the speed of light in the early 1900s, he revealed that space and time are not separate, unchanging backgrounds against which events unfold. Instead, they are woven together into a single fabric that can be stretched, compressed, and warped by motion and gravity. At everyday speeds, these effects are so small that we never notice them. But as you approach the speed of light, strange and wonderful things begin to happen. Time slows down. Distances shrink. The very nature of cause and effect begins to blur. These are not merely theoretical curiosities. They are fundamental features of our universe that have been confirmed by countless experiments and observations. Tonight, we embark on a journey of imagination and scientific exploration. We will delve into the deepest mysteries of space and time, examining what would happen if you possessed the power to move at light speed. We will explore the scientific principles that govern such motion, the paradoxes that arise, and the profound implications for our understanding of reality itself. This is not just a story about speed. It is a story about the nature of existence, about the strange and beautiful universe we inhabit, and about the endless human desire to push beyond the boundaries of what seems possible. As we begin this exploration, we invite you to open your mind to possibilities that may seem impossible, to consider ideas that challenge our everyday experience, and to join us in contemplating one of the most profound questions in science. What would it mean to move at the speed of light? The journey ahead will take us through the fundamental laws of physics, into the realm of quantum mechanics, and out to the farthest reaches of space and time. We will encounter concepts that may seem strange or counterintuitive, but remember that the universe itself is far stranger and more wonderful than our everyday experience suggests. The speed of light is not just a number, it is a key that unlocks some of the deepest secrets of reality. So settle in, relax, and prepare to embark on an extraordinary journey. Tonight, we explore what would happen if you had the power to move at light speed. And in doing so, we may discover something profound about the nature of the universe and our place within it. To understand what it would mean to move at light speed, we must first understand what light itself truly is and why its speed represents the ultimate limit in our universe. Light is not simply the brightness that allows us to see the world around us. It is something far more fundamental, a phenomenon that reveals the deepest structure of reality itself. When we measure the speed of light in a vacuum, we find that it travels at exactly 299,792,458 meters per second. This number is not arbitrary. It is woven into the very fabric of space and time, appearing in the equations that describe everything from the smallest subatomic particles to the largest structures in the cosmos. But light speed is not just about light. It is about information itself. Nothing in the universe can carry information faster than light speed. This means that if you were on the sun and wanted to send a message to Earth, that message would take at least 8 minutes and 20 seconds to arrive, no matter how advanced your technology might be. This is not a limitation of our current understanding or technology. It is a fundamental feature of the universe itself. The story of our understanding of light speed begins centuries ago with curious scientists who wondered how fast light actually moves. In the 1600s, a Danish astronomer named Ole Romer made the first successful measurement of light speed by carefully observing the moons of Jupiter. He noticed that the timing of these moons seemed to change depending on whether Earth was moving toward or away from Jupiter in its orbit. This tiny difference allowed him to calculate that light had a finite speed, though his measurement was not very accurate by today's standards. Over the centuries, scientists developed increasingly sophisticated methods to measure light speed. They used rotating mirrors, spinning wheels, and eventually laser interferometry to pin down this fundamental constant with incredible precision. But as our measurements became more accurate, something remarkable became clear. The speed of light in a vacuum never changes. It is always exactly the same, no matter how fast you are moving when you measure it. This unchanging nature of light speed puzzled scientists for decades. Common sense tells us that if you are running toward a baseball and someone throws it to you, the ball should appear to approach you faster than if you were standing still. But light does not behave this way. Whether you are standing still or racing through space at incredible speeds, light always approaches you at exactly the same speed. This strange behavior of light forced scientists to reconsider their most basic assumptions about space and time. The breakthrough came when Albert Einstein realized that space and time themselves must be flexible. If light speed is always constant, then space and time must stretch and compress to make this possible. This insight led to the development of special relativity, one of the most revolutionary theories in the history of science. Einstein showed that the speed of light is not just a property of light itself, but a fundamental feature of the geometry of space and time. Space and time are not separate entities, but are woven together into a single four-dimensional fabric called space-time. The speed of light represents the maximum rate at which any cause can produce an effect, the ultimate speed limit of the universe. This speed limit applies to everything, not just light. It applies to particles, to energy, to information, and to any form of influence or interaction. Nothing with mass can ever reach light speed, because doing so would require infinite energy. Even massless particles like photons, which make up light, can only travel at this speed, never faster or slower in a vacuum. The implications of this universal speed limit are profound. It means that the universe has a built-in delay system. Events that happen in distant parts of the cosmos cannot immediately affect us. If a star explodes 100 light years away, we will not see or feel the effects of that explosion for 100 years. This creates a kind of cosmic order, preventing the universe from descending into chaos where effects could precede their causes. But the speed of light does more than just set limits. It also connects space and time in ways that our everyday experience cannot prepare us for. When you move very fast, time slows down for you relative to someone who is stationary. When you accelerate, you create a kind of gravity. These effects are tiny at everyday speeds, but they become dramatic as you approach light speed. The speed of light also appears in Einstein's famous equation, E equals mc squared, which shows that mass and energy are interchangeable. This equation reveals that even a tiny amount of mass contains enormous amounts of energy. It explains how stars shine, how nuclear reactions work, and why the sun can continue burning for billions of years. The c in this equation represents the speed of light, squared, showing once again how this fundamental constant appears at the heart of physical reality. As we contemplate what it would mean to move at light speed, we must remember that we are not just talking about moving very fast. We are talking about approaching the fundamental limit of the universe itself, the boundary between what is possible and what is not. At light speed, space and time behave in ways that challenge our deepest intuitions about reality. The speed of light is not just fast. It is the speed at which the universe itself operates. It is the rate at which space and time unfold, the pace at which cause and effect propagate through the cosmos. To move at light speed would be to move at the speed of reality itself, to join the fundamental processes that make the universe possible. Understanding light speed also requires us to think about what light actually is at its most fundamental level. Light is electromagnetic radiation, a wave of electric and magnetic fields that ripple through space itself. But light is also made up of particles called photons, tiny packets of energy that have no mass but carry momentum and energy. This dual nature of light, being both wave and particle, is one of the most mysterious aspects of quantum physics. The electromagnetic spectrum extends far beyond the visible light our eyes can detect. Radio waves, microwaves, infrared radiation, ultraviolet light, X-rays and gamma rays are all forms of electromagnetic radiation, all traveling at the exact same speed through empty space. Whether it is the gentle warmth of sunlight on your face, or the powerful gamma rays from a distant supernova, all electromagnetic radiation moves at light speed. This universality of light speed across all forms of electromagnetic radiation tells us something profound about the nature of space itself. Space is not empty nothingness, but rather a dynamic medium through which electromagnetic fields can propagate. The speed of light is really the speed at which disturbances in the electromagnetic field can travel through this medium we call space. When we talk about reaching light speed, we are really talking about joining this fundamental flow of electromagnetic energy through the universe. Photons, the particles that make up light, experience no passage of time at all. From a photon's perspective, it is created and absorbed in the same instant, even if it travels for billions of years across the cosmos. This timeless existence of light particles gives us a hint of what it might be like to move at light speed. The pursuit of understanding light speed has led to some of the most important technological advances in human history. The global positioning system that helps us navigate relies on precise measurements of the time it takes radio signals to travel from satellites to receivers on Earth. These calculations must account for the effects of relativity, or the system would be off by miles. Fiber optic communications, laser technology, and even the internet itself depend on our understanding of how light behaves and travels. But perhaps most importantly, the speed of light connects us to the cosmos in ways that are both humbling and inspiring. When you look up at the night sky, you are not seeing the stars as they are now, but as they were years, decades, or centuries ago. The light entering your eyes left those distant suns long ago, carrying with it information about the conditions that existed when that light began its journey. The nearest star to our sun, Proxima Centauri, is about 4¼ light years away. This means that the light you see from Proxima Centauri tonight actually left that star over 4 years ago. If Proxima Centauri were to suddenly disappear, we would not know about it for more than 4 years. In this sense, light speed creates a kind of cosmic buffer, a built-in delay that prevents us from experiencing instantaneous changes across the universe. This delay has profound implications for our understanding of simultaneity. Events that appear to happen at the same time for one observer may happen at different times for another observer moving at a different speed. This relativity of simultaneity is one of the most counterintuitive consequences of the finite speed of light, and it challenges our everyday notions of a universal now that it exists everywhere at once. The speed of light also plays a crucial role in the evolution and structure of the universe itself. The cosmic microwave background radiation, the afterglow of the Big Bang, has been traveling through space for over 13 billion years. This ancient light carries information about the early universe, allowing us to peer back in time and understand how the cosmos evolved from its earliest moments. As we contemplate moving at light speed, we must also consider the energy requirements. According to Einstein's theories, accelerating any object with mass to light speed would require infinite energy. This is not merely a practical limitation, but a fundamental impossibility. The faster you go, the more energy is required to accelerate further, and as you approach light speed, the energy requirement grows without bound. Only massless particles like photons can travel at light speed, and they can only travel at this speed, never faster or slower in a vacuum. This suggests that moving at light speed might require fundamentally changing what you are, perhaps transforming from a massive being into pure energy or information. The constancy of light speed also means that it serves as a universal reference point, a cosmic standard against which all motion can be measured. No matter how fast you are moving, light always passes you at the same speed. This creates a kind of cosmic democracy where the laws of physics are the same for all observers, regardless of their motion. Light moves across the universe faster than anything we know, but the mysteries of time and space remain. As we continue our exploration, we will discover that this ultimate speed limit creates some of the most beautiful and puzzling phenomena in all of science. The speed of light is not just a number, it is a doorway to understanding the deepest truths about the nature of existence itself. The relationship between light speed and time is perhaps the most mind-bending aspect of modern physics. Before Albert Einstein revolutionized our understanding in 1905, people believed that time was absolute and universal. Everyone, everywhere in the universe, experienced time flowing at exactly the same rate. A second was a second, an hour was an hour, whether you were sitting in a chair or racing through space at incredible speeds. Einstein showed us that this intuitive view of time is fundamentally wrong. Time is not the steady, unchanging river we once thought it to be. Instead, time is elastic, flexible, and intimately connected to motion and gravity. The faster you move through space, the slower you move through time. This is not a philosophical concept or a mathematical curiosity. It is a measurable, physical reality that affects everything in the universe, including you. Einstein's special theory of relativity revealed that space and time are not separate entities, but are woven together into a single four-dimensional fabric called space-time. When you move through space, you are also moving through time, and the total speed at which you move through space-time is always exactly the speed of light. This means that if you are sitting perfectly still in space, you are moving through time at maximum speed. But if you start moving through space, you must slow down your movement through time to compensate. This trade-off between motion through space and motion through time creates what we call time dilation. The faster you move through space, the slower time passes for you relative to someone who is stationary. At everyday speeds, this effect is so small that it is completely unnoticeable. If you drive across the country at highway speeds, you will age about 1 nanosecond less than someone who stays home. But as you approach the speed of light, time dilation becomes dramatic and impossible to ignore. Imagine you are traveling at 90% of light speed. Time would pass about twice as slowly for you compared to someone at rest. If you traveled for what seemed like 1 year at this speed, 2 years would pass on Earth. At 99% of light speed, time would slow down by a factor of about 7. Your 1-year journey would correspond to 7 years passing on Earth. At 99.9% of light speed, time would slow down by a factor of about 22. As you get closer and closer to light speed, time dilation becomes more and more extreme. At 99.99% of light speed, time would slow down by a factor of about 70. At 99.999% of light speed, time would slow down by a factor of about 223. The pattern continues without end. The closer you get to light speed, the more dramatically time slows down. But what happens when you actually reach light speed? At light speed, time dilation becomes infinite. From the perspective of someone watching you, your clocks would stop completely. You would appear frozen in time, like a photograph. But from your own perspective, something even stranger would happen. You would experience no passage of time at all. The journey from your starting point to your destination would seem to happen instantaneously, regardless of the distance traveled. This is exactly what photons experience. A photon of light leaving a star 1,000 light-years away experiences no time during its journey to Earth. From the photon's perspective, it is emitted and absorbed in the same instant, even though 1,000 years pass on Earth during its journey. This timeless existence is one of the most profound and mysterious aspects of light-speed travel. The mathematics of time dilation involves what physicists call the Lorentz factor, named after the Dutch physicist Hendrik Lorentz. This factor describes how much time slows down as you approach light speed. At low speeds, the Lorentz factor is very close to 1, meaning time passes almost normally. But as you approach light speed, the Lorentz factor grows larger and larger, eventually approaching infinity. Time dilation has been confirmed by countless experiments and observations. Subatomic particles called muons, created when cosmic rays hit Earth's atmosphere, have very short lifespans. They should decay before reaching the ground, but we detect them at sea level because they are moving so fast that time dilation extends their lifespans. Atomic clocks flown on airplanes show measurable time differences compared to identical clocks left on the ground. The global positioning system must account for time dilation effects to maintain accuracy. But time dilation is not just about clocks running slowly. It affects all physical processes. Your heartbeat, your breathing, your thoughts, the chemical reactions in your body, everything would slow down proportionally. From your perspective, nothing would seem different. Your watch would tick normally. Your thoughts would flow at their usual pace. But to an outside observer, you would appear to be moving in slow motion. The implications of time dilation for light speed travel are staggering. If you could somehow reach light speed, you could travel to the most distant galaxies in the universe without experiencing any passage of time. You could journey to a galaxy 10 billion light-years away and arrive instantaneously from your perspective, even though 10 billion years would pass on Earth during your journey. This creates a kind of cosmic time machine. Light-speed travel would allow you to journey far into the future by traveling through space. You could leave Earth today, travel to a distant star system, and return to find that centuries or millennia have passed on Earth while you experienced only a brief journey. This is one way time travel into the future might be possible, though returning to the past would face seemingly insurmountable obstacles. The relationship between light speed and time also reveals something profound about the nature of reality itself. Time is not a universal backdrop against which events unfold, but rather a dimension that can be stretched and compressed just like the dimensions of space. Moving at light speed would place you at the boundary between space and time, where the normal rules of temporal experience break down completely. Einstein's insights about time and light speed have practical applications in our daily lives. The Global Positioning System relies on satellites that orbit Earth at high speeds. These satellites experience time dilation effects that, while small, would cause navigation errors of several miles if not corrected. The Internet, which depends on precise timing synchronization, also must account for relativistic effects in its most sensitive applications. The concept of simultaneous events also becomes problematic at light speed. Events that appear to happen at the same time for one observer may happen at different times for another observer moving at a different speed. This relativity of simultaneity means that the concept of a universal now, a moment that exists everywhere in the universe at once, is an illusion. At light speed, this breakdown of simultaneity becomes complete. The discovery of time dilation fundamentally changed our understanding of what it means to exist in the universe. Before Einstein, scientists believed that time was like a cosmic metronome, keeping the same beat everywhere and for everyone. The revelation that time is relative, that it can slow down and speed up depending on your motion, was so radical that many scientists initially rejected it. Even today, more than a century later, the implications of time dilation continue to challenge our intuitions about reality. To truly understand time dilation, we must think about what time actually is. Time is not just the ticking of a clock or the progression of day and night. Time is the dimension in which cause and effect unfold, the arena in which change and motion become possible. When time slows down, everything slows down with it. The rate of chemical reactions, the oscillation of atoms, the firing of neurons in your brain, all of these processes would decelerate proportionally. This means that consciousness itself would slow down along with time. If you were traveling at 99% of light speed, your thoughts would unfold about 7 times slower than normal from an external perspective. A thought that normally takes 1 second to complete would take 7 seconds from the viewpoint of someone at rest. But you would be completely unaware of this slowdown because your perception of time would slow down by exactly the same factor. The mathematics of time dilation reveals some truly extraordinary possibilities. Consider traveling at 99.9999% of light speed. At this speed, time would slow down by a factor of about 707. This means that if you traveled for what seemed like 1 day at this speed, nearly 2 years would pass on Earth. If you traveled for what seemed like 1 year, about 700 years would pass on Earth. The energy requirements for reaching such speeds are staggering. According to Einstein's famous equation, E equals mc squared, the energy needed to accelerate an object grows without limit as you approach light speed. To accelerate a single kilogram of matter to 99% of light speed would require about 9 times 10 to the 16th joules of energy. This is roughly equivalent to the energy output of a large nuclear power plant, running for several years. But the energy requirements become even more extreme as you get closer to light speed. To accelerate that same kilogram to 99.9% of light speed would require about 32 times 10 to the 16th joules. To reach 99.99% of light speed would require about 100 times 10 to the 16th joules. The energy requirements increase exponentially as you approach light speed, eventually becoming infinite. This infinite energy requirement is not merely a practical limitation, but a fundamental impossibility. It means that no object with mass can ever reach light speed, no matter how advanced our technology becomes. Only massless particles like photons can travel at light speed, and they can only travel at this speed, never faster or slower in a vacuum. The concept of proper time versus coordinate time becomes crucial when discussing light speed travel. Proper time is the time measured by a clock that is moving along with you. Coordinate time is the time measured by a stationary observer watching your journey. As you approach light speed, the difference between these two measurements becomes dramatic. Your proper time might indicate that only minutes have passed, while coordinate time shows that years or decades have elapsed. This difference in time measurements creates what physicists call the twin paradox. Imagine identical twins, one who stays on Earth and one who travels to a distant star at nearly light speed. When the traveling twin returns, they would have aged much less than the twin who stayed on Earth. The traveling twin might have aged only a few years, while the Earth-bound twin aged several decades. This is not science fiction, but a real consequence of time dilation that has been verified by numerous experiments. The twin paradox reveals something profound about the nature of time travel. Light-speed travel offers a one-way ticket to the future. You could travel forward in time by journeying through space at high speeds, but returning to your original time would be impossible. This creates a kind of temporal exile, where light-speed travelers would be forever cut off from their past. Time dilation also affects the perception of distances. As you approach light speed, the distances you travel appear to shrink due to an effect called length contraction. A journey that appears to cover billions of light years to a stationary observer would seem much shorter to you as the traveler. At light speed, all distances would shrink to zero from your perspective, making the entire universe appear to collapse into a single point. The combination of time dilation and length contraction creates a strange symmetry. From your perspective, traveling at light speed, you would traverse any distance instantaneously because both time and space would shrink to zero. From the perspective of a stationary observer, you would take the expected amount of time to cover the distance, but your clocks would appear to stop completely. This symmetry reveals something fundamental about the structure of space-time. Space and time are not separate entities, but are aspects of a single, unified fabric. When you move through space, you're also moving through time, and the total speed at which you move through space-time is always exactly the speed of light. This means that everything in the universe, including you, is already traveling at light speed through space-time. The question is not whether you can reach light speed, but how much of your light speed motion is directed through space versus through time. The implications of this understanding are staggering. Right now, as you sit reading this, you are moving through time at nearly light speed. Almost all of your motion through space-time is directed through the time dimension. But if you were to start moving through space, some of your motion through time would be redirected into spatial motion, causing time to slow down for you. This redistribution of motion through space-time creates what we experience as time dilation. The faster you move through space, the slower you move through time, but your total speed through space-time remains constant. At light speed, all of your motion would be directed through space, leaving none for motion through time. This is why time stops at light speed. The practical implications of time dilation extend far beyond theoretical physics. Modern technology depends on our understanding of how time behaves at high speeds. Particle accelerators routinely accelerate subatomic particles to nearly light speed, and the time dilation effects must be carefully accounted for in the design and operation of these machines. The lifespans of unstable particles are extended by time dilation, allowing scientists to study them in detail. Satellite navigation systems provide another example of how time dilation affects our daily lives. The satellites that make up the Global Positioning System orbit Earth at speeds of about 4 kilometers per second. At these speeds, time dilation causes their clocks to run slow by about 7 microseconds per day. While this might seem insignificant, it would cause navigation errors of several miles if not corrected. The system must continuously adjust for these relativistic effects to maintain accuracy. As we contemplate what it would mean to move at light speed, we must grapple with the fact that we would be entering a realm where time itself behaves in ways that challenge our deepest intuitions. We would be joining the timeless dance of photons, experiencing the universe in a way that no conscious being has ever experienced before. the journey through time would become as real and tangible as the journey through space, and the two would become indistinguishable aspects of a single, unified reality. The relationship between light speed and time forces us to reconsider our most basic assumptions about existence. Time is not a universal constant, but a flexible dimension that can be stretched and compressed. At light speed, we would reach the ultimate boundary of this flexibility, where time itself ceases to flow and the universe becomes a single, eternal moment. When we begin to seriously contemplate what it would mean to move at light speed, we encounter some of the most puzzling and counterintuitive consequences in all of science. These are not merely theoretical curiosities, but fundamental challenges to our understanding of cause and effect, simultaneity, and the very nature of reality itself. The paradoxes that emerge from light-speed travel force us to question our most basic assumptions about how the universe works. Perhaps the most famous of these paradoxes is what physicists call the relativity of simultaneity. In our everyday experience, we take it for granted that events either happen at the same time or they do not. If two lightning bolts strike at exactly noon, we assume they are simultaneous for everyone, everywhere. But Einstein's theory of relativity reveals that simultaneity is not absolute, but depends on your motion through space. Imagine you are standing on a train platform, watching a very long train pass by at high speed. Lightning strikes both the front and back of the train at exactly the same moment from your perspective on the platform. You see the lightning bolts as perfectly simultaneous, but someone riding in the middle of the train would see something completely different, because they are moving toward the front lightning bolt and away from the back lightning bolt. The light from the front strike reaches them before the light from the back strike. From their perspective, the front lightning bolt happens first. This is not simply a matter of perception or the finite speed of light creating delays. The order of events actually changes depending on your motion. Events that are simultaneous for one observer happen at different times for another observer moving at a different speed. As you approach light speed, this effect becomes more and more dramatic, eventually leading to situations where cause and effect themselves become ambiguous. The breakdown of simultaneity at light speed creates what physicists call causality violations. In our normal experience, causes always precede their effects. You flip a light switch and then the light turns on. You throw a ball and then it travels through the air. But at light speed, the normal ordering of cause and effect can become scrambled. Effects might appear to happen before their causes, creating logical paradoxes that challenge our understanding of how the universe operates. Consider the famous grandfather paradox in A New Light. Imagine you could travel faster than light to a distant star, then return to Earth. Because of the relativity of simultaneity at such extreme speeds, you might arrive back on Earth before you left. This creates the possibility of meeting yourself, or even preventing your own journey from ever beginning. The paradox arises because your return trip could interfere with the very events that made your journey possible in the first place. At light speed itself, the concept of simultaneity breaks down completely. From the perspective of a photon, all events along its path happen simultaneously. The emission from a distant star and the absorption by your eye happen at the same instant from the photon's point of view. This collapse of temporal ordering creates a reality where past, present, and future become indistinguishable. Another profound paradox emerges when we consider the length contraction that occurs at light speed. As you approach light speed, distances in the direction of your motion appear to shrink. At light speed, all distances shrink to zero from your perspective. This means that from your point of view, the entire universe would collapse into a single point. You would simultaneously exist everywhere and nowhere, experiencing all locations in the universe as a single, unified place. This spatial paradox creates some mind-bending scenarios. If you were traveling at light speed from Earth to a star 100 light years away, the journey would cover 100 light years from the perspective of someone on Earth. But from your perspective, the distance would be 0. You would experience arriving at your destination the instant you departed, even though a century would pass on Earth during your journey. The combination of time dilation and length contraction at light speed creates what we might call the paradox of universal presence. You would exist at all points along your path simultaneously, stretched across space in a way that defies our normal understanding of what it means to be in a particular place at a particular time. Your consciousness, if it could somehow survive such conditions, would span vast regions of space while experiencing no passage of time. The energy paradoxes of light-speed travel are equally perplexing. As we have discussed, accelerating any object with mass to light speed would require infinite energy. But even if we could somehow overcome this limitation, what would happen to that infinite energy when you arrived at your destination? Energy cannot simply disappear, so where would it go? The conservation of energy, one of the most fundamental principles in physics, seems to break down at light speed. Some physicists have proposed that traveling at light speed might require converting matter into pure energy, then reconverting that energy back into matter at the destination. But this process raises its own paradoxes. Would the reconstructed matter be the same as the original? Would consciousness survive such a transformation? These questions touch on deep philosophical issues about the nature of identity and what it means to be you. The information paradoxes of light-speed travel are perhaps even more troubling. At light speed, information itself behaves in strange ways. Because simultaneity breaks down, information about events might arrive before the events themselves occur. This could create closed causal loops where information has no ultimate source, appearing to come from nowhere and generating itself in an endless cycle. Consider a scenario where you travel at light speed to deliver a message to the past. The recipient of that message uses the information to prevent the very situation that motivated you to send the message in the first place. Where did the information originally come from? This creates what physicists call a bootstrap paradox, where information or objects exist without ever being created. The quantum mechanical aspects of light-speed travel introduce additional paradoxes. Quantum mechanics tells us that particles can exist in multiple states simultaneously until they are observed. But observation requires the exchange of information, which cannot travel faster than light. At light speed, the normal rules of quantum observation might break down, creating situations where particles exist in impossible superpositions of states. These quantum paradoxes become even more complex when we consider quantum entanglement. Entangled particles can instantly affect each other regardless of the distance between them, seemingly violating the speed of light limit for information transfer. But quantum mechanics carefully prevents this from being used to send information faster than light. At light speed itself, these careful restrictions might break down, potentially allowing for true faster-than-light communication. The mathematical frameworks we use to describe light-speed travel also reveal deep paradoxes. The equations of special relativity involve division by 0 when describing motion at exactly light speed, leading to mathematical infinities that have no clear physical interpretation. These infinities suggest that light speed represents a fundamental boundary in the structure of space-time itself, a boundary that cannot be crossed by anything with mass. Some physicists have speculated about the existence of hypothetical particles called tachyons that always travel faster than light, but tachyons would experience time flowing backward and would exhibit causality violations that make their existence highly problematic. The paradoxes associated with tachyons are so severe that most physicists doubt they could exist in our universe. The paradoxes of light-speed travel also challenge our understanding of consciousness and identity. If time stops at light speed, how could consciousness continue to function? Consciousness seems to require the passage of time to process information and maintain continuity of experience. At light speed, the very concept of conscious experience might become meaningless. Even more fundamentally, the paradoxes force us to question whether the concept of traveling at light speed makes any sense at all for objects with mass. Perhaps these paradoxes are nature's way of telling us that light speed is fundamentally reserved for massless particles like photons. The paradoxes might not be problems to be solved, but rather indications that we are asking impossible questions. The philosophical implications of these paradoxes extend far beyond physics. They challenge our notions of free will, causality, and the nature of existence itself. In a universe where effects can precede their causes and where simultaneity is relative, do we truly have control over our actions? Are we responsible for consequences that might occur before we make our decisions? As we contemplate these paradoxes, we begin to see that light speed represents more than just a very fast velocity. It represents a fundamental boundary in the structure of reality, a threshold beyond which the normal rules of physics and logic begin to break down. The paradoxes are not flaws in our theories, but windows into the deepest mysteries of existence, revealing the strange and wonderful nature of the universe we inhabit. Perhaps the greatest paradox of all is that light itself, which travels at light speed, somehow manages to avoid all of these logical contradictions. Photons experience no time, traverse no distance, and exist in a timeless realm that transcends the paradoxes that would plague any massive object attempting to reach light speed. In the end, the paradoxes of light speed travel might be teaching us that light speed is not a destination to be reached, but a fundamental aspect of reality to be appreciated and understood. The human body is a marvel of biological engineering, finely tuned by millions of years of evolution to function within the gentle confines of Earth's environment. Every cell, every organ, every biological process has evolved under the assumption that we will never move faster than a few dozen kilometers per hour for extended periods. But what would happen to this delicate biological machinery if it were somehow subjected to the extreme conditions of light speed travel? The answer reveals just how extraordinary and impossible such a journey would be for any living creature. To understand the physical effects of light speed travel, we must first consider what happens to matter itself as it approaches these incredible velocities. According to Einstein's theory of special relativity, the mass of any object increases dramatically as it approaches light speed. This is not simply a matter of gaining weight in the conventional sense, but rather a fundamental change in the object's resistance to acceleration. The faster you go, the more energy is required to make you go even faster. At everyday speeds, this increase in mass is completely negligible. Even at the speed of a jet aircraft, the increase would be far too small to measure with the most sensitive instruments. But as you approach light speed, the effect becomes dramatic. At 90% of light speed, your mass would be about 2.3 times greater than your rest mass. At 99% of light speed, your mass would be about 7 times greater. At 99.9% of light speed, your mass would be about 22 times greater than normal. This increase in mass would have profound effects on your body. Your bones, which evolved to support your normal body weight, would suddenly be required to support many times that weight. Your heart, which normally pumps blood through your circulatory system with relative ease, would struggle against the increased mass of your blood. Every movement would become extraordinarily difficult as your muscles attempted to move limbs that had become many times heavier than normal. But the mass increase is just the beginning of the physical challenges. The energy required to accelerate your body to light speed would be enormous beyond comprehension. A typical human body has a mass of about 70 kilograms. To accelerate this mass to just 90% of light speed would require about 8 times 10 to the 18th joules of energy. This is roughly equivalent to the total energy output of the entire United States for about 6 months. To put this in perspective, This amount of energy could power every home in America for half a year, or it could be used to accelerate a single human being to 90% of light speed. As you approach closer to light speed, the energy requirements grow exponentially. To reach 99% of light speed would require about 50 times 10 to the 18th joules. To reach 99.9% would require about 150 times 10 to the 18th joules. To actually reach light speed would require infinite energy. Where would this enormous amount of energy come from? And more importantly, where would it go? The human body is not designed to handle such vast quantities of energy. The chemical processes that power our cells involve energies measured in tiny fractions of a joule. Subjecting the body to the energies required for light-speed travel would be like trying to power a delicate watch with a nuclear reactor. The result would be instant and complete destruction of every biological structure. Even if we could somehow solve the energy problem, the acceleration process itself would present insurmountable challenges. The human body can only withstand a limited amount of acceleration before suffering serious injury or death. Fighter pilots, who experience some of the highest accelerations encountered by humans, can briefly withstand about 9 times the acceleration of gravity before losing consciousness. Sustained accelerations of even a few times gravity can cause permanent damage to the cardiovascular system and other organs. To reach light speed in any reasonable amount of time would require accelerations many millions of times greater than what the human body can survive. Even if the acceleration were spread out over many years to keep it within survivable limits, the sheer duration required would present its own problems. It would take thousands of years of continuous acceleration at the maximum survivable rate to reach even a small fraction of light speed. The effects of such prolonged acceleration would be devastating to the human body. Bones would gradually weaken under the constant stress. The cardiovascular system would be damaged by years of working against increased apparent weight. The brain, which is particularly sensitive to acceleration forces, would suffer irreversible damage long before reaching significant fractions of light speed. But let us imagine, for the sake of argument, that these acceleration problems could somehow be overcome. What would happen to your body once you actually reached light speed? At light speed, according to the laws of physics, your mass would become infinite. An infinite mass concentrated in the finite volume of a human body would create gravitational effects so extreme that space and time around you would be severely distorted. Your infinite mass would generate an infinite gravitational field, potentially creating what physicists call a naked singularity. This would be similar to a black hole, but without the protective event horizon that normally hides the singularity from the outside universe. The gravitational forces would be so intense that they would tear apart the fabric of space-time itself, creating unpredictable and potentially catastrophic effects throughout the universe. The electromagnetic effects of light speed travel would be equally devastating. As your body approached light speed, the electromagnetic fields generated by the motion of the charged particles in your cells would become incredibly intense. These fields would interact with the electromagnetic radiation pervading space, creating what physicists call synchrotron radiation. This high-energy radiation would cook your body from the inside out, destroying every biological molecule. The quantum mechanical effects of light speed travel introduce additional complications. At the quantum level, particles have properties that are described by probability waves. As you approach light speed, these quantum effects become more pronounced. The uncertainty principle, which describes the fundamental limits on our ability to know both the position and momentum of particles, becomes increasingly important. At light speed, the quantum uncertainty in your position would become so large that your body would effectively exist everywhere and nowhere simultaneously. The atoms that make up your body would be smeared out across vast regions of space, losing any resemblance to the organized structures that define living tissue. Your consciousness, which depends on the precise organization of neurons in your brain, would cease to exist in any meaningful sense. The biological processes that sustain life would face insurmountable challenges at light speed. Cellular respiration, the process by which your cells extract energy from food, depends on precise chemical reactions that occur at specific rates. At light speed, time dilation would slow these reactions to a complete stop from an external perspective. Your metabolism would cease, your heart would stop beating, and your brain would stop functioning. But from your own perspective, traveling at light speed, something even stranger would happen. You would experience no passage of time at all. The entire journey, regardless of distance, would seem to happen instantaneously. You would have no opportunity to breathe, to think, or to experience anything during the journey. In a very real sense, you would cease to exist as a conscious being for the duration of your light speed travel. The molecular structure of your body would also face severe challenges. The strong forces that hold atomic nuclei together and the electromagnetic forces that bind atoms into molecules are carefully balanced under normal conditions. At light speed, these force balances would be severely disrupted. The increased energy of your motion would be comparable to the binding energies that hold matter together, potentially causing your body to disintegrate at the molecular level. Temperature effects would add another layer of complications. As you approach light speed, your kinetic energy would become enormous. This energy would manifest as heat when you eventually slowed down or encountered any resistance. The amount of heat generated would be sufficient to vaporize your body many times over. You would literally burn up from the inside out as your kinetic energy was converted to thermal energy. The interaction with the cosmic microwave background radiation would create additional heating effects. This faint radiation, left over from the Big Bang, pervades all of space. At rest, this radiation is barely detectable and has no significant effect on biological systems. But at light speed, this radiation would appear blue shifted to extremely high energies, bombarding your body with what would effectively be intense gamma rays. The magnetic fields pervading space would also interact dangerously with your body at light speed. Earth's magnetic field, which normally provides beneficial protection from cosmic radiation, would appear enormously amplified from your perspective. The iron in your blood would be subject to magnetic forces strong enough to disrupt circulation and potentially tear apart blood vessels. Even the vacuum of space itself would become hostile at light speed. What we normally think of as empty space is actually filled with virtual particles that constantly pop into and out of existence, according to quantum mechanics. At light speed, your interaction with these virtual particles would generate intense radiation and create drag forces that would slow you down and heat you up. Perhaps most fundamentally, the very concept of a biological body traveling at light speed may be contradictory. Life, by its very nature, requires time to unfold. Biological processes need duration to occur. Growth, healing, thinking, and all other life functions depend on the passage of time. At light speed, where time stops completely, life itself becomes impossible. The physical effects we have described paint a picture of complete incompatibility between biological life and light speed travel. Every aspect of your body, from the quantum mechanical behavior of subatomic particles to the gross anatomy of organs and tissues, would be fundamentally disrupted by attempting to reach light speed. The forces involved are so far beyond anything the human body could survive that light speed travel represents not just a technological challenge, but a fundamental impossibility for any form of matter-based life. The universe is almost incomprehensibly vast. Our own galaxy, the Milky Way, spans about 100,000 light-years from edge to edge. The nearest major galaxy, Andromeda, lies over 2.5 million light-years away. The observable universe extends for over 93 billion light-years in all directions, containing hundreds of billions of galaxies, each with hundreds of billions of stars. Crossing such distances at ordinary speeds would take longer than the age of the universe itself. But what if you could move at light speed? Could you truly cross the universe in an instant, making the vast cosmos seem no larger than your neighborhood? To understand what lightspeed travel would mean for crossing cosmic distances, we must first grasp the true scale of the universe. Light from the sun takes about 8 minutes and 20 seconds to reach Earth. This might seem fast, but it means that if the sun suddenly disappeared, we would continue to see it shining for over 8 minutes before the darkness arrived. The nearest star beyond our solar system, Proxima Centauri, is about 4.25 light-years away. Even traveling at light speed, a journey to this nearest stellar neighbor would take over 4 years from the perspective of someone watching from Earth. But here is where the strange physics of light speed travel becomes truly remarkable. While the journey to Proxima Centauri would indeed take 4.25 years as measured by clocks on Earth, the experience for someone traveling at light speed would be completely different. Due to the extreme time dilation that occurs at light speed, the traveler would experience no passage of time at all during the journey. From their perspective, they would arrive at Proxima Centauri at the exact same instant they departed from Earth, regardless of the 4-year journey time measured by Earth-based observers. This instantaneous travel experience becomes even more extraordinary when we consider journeys to truly distant destinations. The center of our galaxy lies about 26,000 light-years from Earth. A light-speed journey to the galactic center would take 26,000 years from Earth's perspective, but the traveler would experience arriving there instantly. The same would be true for a journey to the Andromeda Galaxy, 2.5 million light-years away, or even to the edge of the observable universe, over 46 billion light-years distant. From the perspective of a light-speed traveler, the entire observable universe would become accessible instantaneously. Every galaxy, every star, every planet would be reachable in 0 time. The vast cosmos that seems to stretch beyond imagination when viewed from our earthbound perspective would collapse into a single, infinitely accessible realm where distance becomes meaningless. But this instantaneous travel comes with a profound cost. While you could reach any destination in the universe instantly from your own perspective, the rest of the universe would age dramatically during your journey. A trip to a galaxy 1 billion light-years away would take 1 billion years from the perspective of Earth. When you arrived at your destination, the Earth you left behind would have aged by 1 billion years. The sun would have evolved into a red giant and then a white dwarf. Life on Earth, if it still existed at all, would be unrecognizably different from what you remembered. This creates a form of temporal exile for light-speed travelers. You could journey instantly to the most distant reaches of the universe, but you could never return to the time and place you left behind. Each journey would carry you further into the future, making you a refugee from your own past. The universe would become accessible in space, but forever lost in time. The effects of light speed travel on space itself are equally profound. According to Einstein's theory of special relativity, objects contract in length as they approach light speed. This length contraction becomes extreme at light speed itself. From your perspective as a light speed traveler, all distances in the direction of your motion would shrink to 0. The 100,000 light-year diameter of our galaxy would appear to have no thickness at all. The billions of light-years separating distant galaxies would collapse to nothing. This contraction of space creates a strange paradox. From your perspective, you would not be traveling through space at all, because there would be no space to travel through. All points along your path would appear to occupy the same location. You would simultaneously exist at your starting point, your destination, and every point in between. The journey would not involve moving from one place to another, but rather experiencing all places as a single, unified location. The implications of this spatial collapse are mind-bending. If you were traveling at light speed from Earth to a distant galaxy, you would experience Earth, every star system along the way, and your final destination as occupying the same point in space. The entire universe in the direction of your travel would appear compressed into a single, infinitely thin plane. You would exist everywhere and nowhere at the same time. This compression of space also affects the geometry of the universe itself. The universe has a complex geometric structure that includes curvature due to the presence of matter and energy. At light speed, this geometric structure would appear completely flattened in the direction of your motion. The curvature of space-time that normally guides the motion of planets, stars, and galaxies would vanish from your perspective. The combination of time dilation and length contraction at light speed creates what physicists call the invariance of the space-time interval. While space contracts to zero and time dilates to infinity, the combination of space and time remains well defined. This mathematical relationship preserves the structure of causality and ensures that the laws of physics remain consistent even under the extreme conditions of light-speed travel. But what about the practical aspects of navigating the universe at light speed? How would you choose your destination when all of space appears collapsed into a single point? How would you avoid colliding with stars, planets, and other objects that normally occupy the space between your starting point and destination? These questions reveal some of the deeper mysteries of light-speed travel. From your perspective at light speed, navigation would become meaningless because direction would lose its normal meaning. All destinations would appear to be in the same place. The concept of steering or changing course would not apply because there would be no spatial separation between different paths. You would not travel through space, but rather exist in a state where all of space is compressed into your immediate vicinity. The question of collisions becomes equally strange. Normally, objects traveling through space must navigate around obstacles like planets and stars. But at light speed, these obstacles would appear to have zero thickness in the direction of your motion. From your perspective, planets would appear as infinitely thin disks that occupy no space along your path. Stars would become lines with no width. The entire three-dimensional structure of the universe would collapse into a two-dimensional projection. Yet this raises a profound question about what happens when you encounter matter during light-speed travel. If you were to collide with a planet or star during your journey, the consequences would be catastrophic beyond imagination. Your infinite kinetic energy would interact with the matter in the obstacle, potentially annihilating both you and the object in a release of energy that would dwarf the most powerful supernovas. The electromagnetic effects of light-speed travel would also dramatically alter your perception of the universe. As you approach light speed, the light from objects ahead of you would be blue, shifted to higher and higher energies, while light from objects behind you would be red, shifted to lower energies. At light speed, this effect would become extreme. Light from stars ahead of you would be blue, shifted into gamma rays, while light from stars behind would be red, shifted into radio waves. This extreme Doppler shifting would completely change the appearance of the universe. Stars that normally shine with visible light would become invisible to your eyes, replaced by intense sources of gamma radiation ahead and radio sources behind. The familiar constellations and cosmic landmarks would disappear, replaced by a universe that glows with high-energy radiation in the direction of your motion and fades to darkness behind you. The cosmic microwave background radiation, the faint afterglow of the Big Bang that permeates all of space, would also be dramatically affected. This normally uniform radiation would appear concentrated into an intense beam of gamma rays ahead of you. The temperature of this radiation, normally just 3 degrees above absolute zero, would appear to reach millions of degrees due to the blue shifting effect. The gravitational effects of light-speed travel add another layer of complexity to cosmic journeys. As your mass increases toward infinity, your gravitational field would become correspondingly strong. This intense gravity would distort the space-time around you, potentially affecting the paths of planets and stars as you pass by. Your passage through the universe might leave behind a wake of gravitational disturbances that could alter the orbits of celestial objects for millions of years. The expansion of the universe itself becomes relevant for truly cosmic journeys. The universe is expanding, causing distant galaxies to recede from us at speeds that can approach light speed. For the most distant observable galaxies, this recession velocity is already a significant fraction of light speed. If you were traveling at light speed towards such a galaxy, you would be racing against the expansion of space itself. This raises fascinating questions about whether you could actually reach the most distant parts of the observable universe. While you would experience the journey instantaneously, the universe would continue expanding during the time it takes light to cross such vast distances. By the time you arrived at your destination, the universe might have expanded so much that other distant galaxies would have moved even further away, potentially beyond the reach of future light-speed journeys. The concept of simultaneity becomes completely meaningless at light speed. Events that appear to happen in sequence for stationary observers would all appear to happen simultaneously for you. The birth and death of stars, the formation and destruction of planets, the evolution of entire civilizations would all be compressed into a single instant. You would witness billions of years of cosmic history unfolding in no time at all. Perhaps most remarkably, light-speed travel would allow you to witness the universe from a completely unique perspective. No other form of matter can travel at light speed, which means that the view from light speed is reserved exclusively for photons themselves. By joining the realm of light, you would see the universe as light sees it, existing in a timeless state where all of space is compressed into a single point and all of history happens at once. The ability to cross the universe instantly at light speed represents the ultimate freedom of movement, but it comes at the ultimate cost in terms of connection to any particular time or place. You would become a citizen of the entire universe, but an exile from any specific moment in its history. The cosmos would shrink to nothing in space, but expand to encompass all of time, creating a form of existence that transcends our normal understanding of what it means to inhabit the universe. At the heart of Einstein's revolution in physics lies one of the most profound insights about the nature of reality. Space and time are not separate, independent entities, but are woven together into a single, unified fabric called space-time. This four-dimensional continuum forms the stage upon which all physical events unfold, from the smallest quantum interactions to the grandest cosmic phenomena. But what happens to this fundamental fabric when you reach the ultimate speed limit of the universe? What occurs to the very structure of reality when you achieve light speed? To understand the implications of reaching light speed for the space-time continuum, we must first appreciate how profoundly different this unified fabric is from our everyday intuitions. In our normal experience, space seems solid and unchanging, while time flows steadily forward at a constant rate. We think of space as the stage and time as the universal clock that measures the progression of events. But Einstein revealed that this separation is an illusion created by our limited perspective. Space-time is more like a flexible membrane that can be stretched, compressed, twisted, and curved. When you move through space, you are also moving through time, and the faster you travel through one dimension, the slower you travel through the other. This trade-off between spatial motion and temporal motion is governed by the fundamental geometry of space-time itself, and it reaches its ultimate expression at light speed. The mathematical description of space-time reveals that every object in the universe has what physicists call a four-velocity. This 4 velocity describes how fast something moves through all 4 dimensions of spacetime combined. The remarkable discovery is that this 4 velocity is always exactly the same for every object in the universe. Everything moves through spacetime at exactly light speed, including you, right now, as you listen to these words. This might seem impossible given that you are probably sitting still, but the key insight is that almost all of your motion through spacetime is currently directed through the time dimension. You are racing through time at nearly light speed, with only a tiny fraction of your spacetime motion directed through the spatial dimensions. When you get up and walk across the room, you are not adding to your total speed through spacetime, but rather redirecting a small portion of your temporal motion into spatial motion. This redistribution of motion through spacetime is what creates the phenomena of time dilation and length contraction that we observe at high speeds. As you move faster through space, you must move correspondingly slower through time to maintain your constant total speed through spacetime. The faster you go spatially, the slower your personal time flows, relative to someone who is moving more slowly through space. At light speed, this redistribution reaches its absolute limit. All of your motion through spacetime would be directed through the spatial dimensions, leaving none for motion through time. This is why time stops completely at light speed. You would not be moving faster than the speed of light through spacetime. You would be moving at the speed of light through spacetime in a purely spatial direction. This complete redirection of spacetime motion from time to space creates profound changes in the structure of reality itself. From your perspective at light speed, the time dimension would effectively cease to exist. Past, present, and future would collapse into a single, eternal moment. All events that ever happened or ever will happen along your path of motion would occur simultaneously in your reference frame. The spatial dimensions would undergo equally dramatic transformations. In the direction of your motion, all distances would contract to zero. The universe would become infinitely compressed, with all points along your path occupying the same location. You would exist simultaneously at every point in the universe that lies in the direction of your travel, experiencing the entire cosmos as a single, unified point. But what happens to the curvature of spacetime when you reach light speed? Einstein's general theory of relativity tells us that matter and energy curve the fabric of spacetime, creating what we experience as gravity. Massive objects like stars and planets create dimples and curves in spacetime that guide the motion of other objects. But at light speed, your energy density would become infinite, potentially creating infinite curvature in spacetime. This infinite curvature could fundamentally alter the geometric structure of the universe. The smooth, continuous fabric of spacetime might develop what mathematicians call singularities, points where the normal rules of geometry break down completely. These singularities would be similar to those found at the centers of black holes, but unlike black hole singularities, they would not be hidden behind event horizons. The creation of naked singularities through light speed travel could have catastrophic consequences for the stability of spacetime itself. The infinite curvature might propagate outward from your location, potentially tearing holes in the fabric of reality. These tears could disconnect different regions of the universe from each other, fundamentally altering the causal structure that allows events in one location to influence events in another. The quantum mechanical properties of spacetime add another layer of complexity to light speed travel. At the smallest scales, spacetime itself exhibits quantum fluctuations, constantly bubbling with virtual particles and energy variations. These quantum effects are normally negligible at macroscopic scales, but the infinite energy density associated with light speed travel might amplify them dramatically. The amplified quantum fluctuations could cause space-time to become fundamentally unstable at light speed. The smooth, continuous fabric might break down into a foam-like structure where the normal concepts of distance and duration lose their meaning. You might find yourself existing in a realm where the basic geometric properties that define space and time fluctuate wildly from moment to moment. The relationship between matter and space-time would also be fundamentally altered at light speed. In normal circumstances, matter moves through space-time, following paths determined by the curvature created by other matter and energy. But at light speed, the distinction between you and space-time itself might disappear. You would not be moving through space-time, but rather becoming part of the space-time fabric itself. This merger with space-time could transform you from a localized object into a geometric feature of the universe itself. Rather than existing at a particular location and time, you might become stretched across space-time like a wrinkle or fold in the fabric of reality. Your consciousness, if it could somehow survive such a transformation, would be distributed throughout space-time rather than concentrated in a specific brain or body. The information content of space-time would also be affected by light-speed travel. Every region of space-time can be thought of as containing information about the events that occur within it. This information is encoded in the geometric properties of space-time itself, in the curvature and connections that define how different points relate to each other. At light speed, the infinite energy density might corrupt or destroy this information storage capacity. The loss of information storage in space-time could have profound implications for the nature of reality. If space-time can no longer reliably encode information about past events, the very concept of history might become meaningless. The universe might lose its ability to maintain a coherent record of what has happened, leading to a reality where only the present moment has any definite existence. The topology of space-time, the way different regions connect to each other, could also be altered by light-speed travel. Normally, space-time has a simple topology where every point is connected to its neighbors in a smooth, continuous way. But the extreme distortions created by infinite energy density might create topological defects, places where space-time develops holes, twists, or connections that violate the normal rules of geometry. These topological changes could create shortcuts through space-time, allowing for forms of travel that bypass the normal limitations of distance and duration. You might emerge from light-speed travel to find that you have created wormholes or other exotic space-time structures that connect distant regions of the universe. These structures could persist long after your journey ends, permanently altering the geometric landscape of space-time. The concept of causality, the principle that causes must precede their effects, depends on the orderly structure of space-time. Events can only influence other events if space-time provides a path connecting them that respects the flow of time. But at light speed, where time stops and space collapses, the normal causal structure breaks down completely. Effects might precede their causes, or events might become their own causes in closed causal loops. This breakdown of causality could create paradoxes that threaten the logical consistency of the universe. Information might flow backward in time, allowing effects to prevent their own causes. Objects might spring into existence without any source or disappear without any explanation. The orderly progression of cause and effect that makes the universe comprehensible might dissolve into chaos. The dimensional structure of space-time itself might be affected by light-speed travel. While we normally experience 3 dimensions of space and 1 dimension of time, theoretical physics suggests that additional dimensions might exist at scales too small to observe directly. The extreme energies associated with light-speed travel might provide access to these hidden dimensions, fundamentally changing the dimensionality of your existence. Entry into higher dimensional spaces could radically alter your perception and experience of reality. Properties that seem fixed and unchangeable in our 4-dimensional space-time might become fluid and variable in higher dimensions. The very concepts of distance, duration, and identity might take on completely new meanings as you gain access to degrees of freedom that do not exist in normal space-time. The ultimate fate of space-time during light-speed travel remains one of the deepest mysteries in theoretical physics. Some possibilities include the complete collapse of the space-time fabric, the creation of new universes through dimensional splitting, or the transformation of space-time into a fundamentally different type of geometric structure. Each of these possibilities would represent a profound change in the nature of reality itself. Perhaps most remarkably, reaching light speed might reveal that space-time is not the fundamental reality we have assumed it to be. Just as Einstein showed that space and time are aspects of a deeper unity, light-speed travel might reveal that space-time itself is an emergent property of something even more fundamental. You might discover that the fabric of reality has layers and depths that we cannot even imagine from our current perspective. The journey to light speed would thus be more than a voyage through space and time. It would be an expedition to the very foundations of existence itself. You would not simply be traveling fast. You would be probing the deepest structures that make reality possible. In reaching light speed, you might discover that the universe is far stranger and more wonderful than we have ever dared to imagine. The quantum realm represents one of the most mysterious and counterintuitive aspects of physical reality. At the smallest scales of existence, the familiar rules of classical physics give way to a strange world where particles exist in multiple states simultaneously, where the act of observation changes reality, and where distant objects can influence each other instantaneously through mysterious quantum connections. When we consider what would happen to these quantum phenomena at light speed, we enter territory that challenges not only our understanding of physics, but our very concepts of existence and reality. To understand how quantum mechanics would be affected by light-speed travel, we must first appreciate the fundamental strangeness of the quantum world. Unlike the classical objects of our everyday experience, quantum particles do not have definite properties until they are measured. An electron, for example, does not have a specific location or momentum until we observe it. Instead, it exists in what physicists call a superposition of all possible states, with each possibility having a certain probability of being observed. This quantum superposition is not merely a limitation of our knowledge, but a fundamental feature of reality at the smallest scales. The electron truly exists in multiple locations simultaneously until the moment of measurement forces it to collapse into a single, definite state. This collapse of the quantum wave function is one of the most mysterious processes in physics, and it becomes even more puzzling when we consider what would happen to it at light speed. The process of quantum measurement requires the exchange of information between the measuring device and the quantum system being observed. This information exchange cannot occur faster than the speed of light, which creates a fundamental limit on how quickly quantum measurements can be performed. But what happens when the quantum system itself is moving at light speed? How can measurement occur when time dilation effects become infinite? At light speed, the normal process of quantum measurement might break down completely. From the perspective of a quantum particle traveling at light speed, no time passes during its journey. This means that the particle would have no opportunity to interact with measuring devices or to exchange the information necessary for wave function collapse. The particle might remain in its superposition state indefinitely, never collapsing into a definite reality. This permanent superposition could create quantum objects that exist in all possible states simultaneously, without ever resolving into specific outcomes. A quantum particle traveling at light speed might simultaneously exist at every possible location along its path, with every possible momentum and in every possible energy state. Such objects would represent a form of quantum immortality, forever suspended in the realm of pure possibility. The wave-particle duality of quantum objects becomes even more mysterious at light speed. Light itself exhibits this duality, behaving sometimes like a wave and sometimes like a particle depending on how it is observed. But light always travels at light speed, which suggests that wave-particle duality might be fundamentally connected to light speed motion. When massive objects reach light speed, they might acquire the same wave-particle duality that characterizes light. This acquisition of wave-like properties could transform matter in profound ways. A human body traveling at light speed might spread out like a wave, existing as a quantum superposition across vast regions of space. Your consciousness might become distributed throughout this quantum wave, experiencing all possible states of existence simultaneously. You would not be a single definite person, but rather a quantum cloud of possibilities. The uncertainty principle, one of the cornerstones of quantum mechanics, states that there are fundamental limits to how precisely we can know certain pairs of properties of quantum objects. The more precisely we know a particle's position, the less precisely we can know its momentum, and vice versa. This uncertainty is not due to limitations in our measuring instruments, but is a fundamental feature of quantum reality. At light speed, the uncertainty principle takes on extreme characteristics. The momentum of a light speed object becomes infinite, which means that the uncertainty in its position also becomes infinite according to the uncertainty principle. This infinite position uncertainty means that the object exists everywhere and nowhere simultaneously, spread throughout the entire universe as a quantum wave. This infinite spreading of quantum existence could fundamentally alter the nature of identity and consciousness. If you were traveling at light speed, your quantum wave function would be smeared across the entire cosmos. Your thoughts, memories, and experiences might exist simultaneously in every galaxy, every star system, and every planet in the universe. You would become a truly cosmic consciousness, experiencing reality from every possible perspective at once. The quantum tunneling effect provides another fascinating aspect of light-speed quantum mechanics. In the quantum world, particles can sometimes pass through barriers that should be impenetrable according to classical physics. This tunneling effect depends on the wave-like nature of quantum objects and becomes more probable when particles have higher energies. At light speed, where kinetic energy becomes infinite, quantum tunneling might become not just probable, but inevitable. Infinite quantum tunneling could allow light-speed travelers to pass through any barrier, no matter how thick or dense. You could tunnel through planets, stars, or even black holes without any resistance. The solid matter that normally forms obstacles to motion would become transparent to your quantum wave function. You would exist in a realm where all barriers disappear and all of space becomes equally accessible. Quantum entanglement represents one of the most mysterious aspects of quantum mechanics. When two particles become entangled, they remain connected in a way that transcends space and time. Measuring one particle instantly affects the other, regardless of the distance between them. Einstein famously called this spooky action at a distance, and it continues to puzzle physicists today. At light speed, quantum entanglement might take on even stranger characteristics. The infinite time dilation could allow entangled particles to maintain their connection across arbitrarily large distances and time periods. You might become entangled with every quantum system you encounter during light-speed travel, creating a web of quantum connections that spans the entire universe. This cosmic quantum entanglement could give you access to information from every corner of the universe simultaneously. Through your entangled connections, you might be able to experience events happening in distant galaxies, sense the formation of new stars, or witness the death of ancient suns. You would become a quantum antenna, receiving information from across the cosmos through the mysterious channels of quantum entanglement. The concept of quantum fields becomes particularly relevant for light-speed travel. According to quantum field theory, what we think of as empty space is actually filled with quantum fields that permeate all of reality. These fields constantly fluctuate, creating virtual particles that pop into and out of existence. At light speed, your interaction with these quantum fields would become extreme. The infinite energy of light speed motion would strongly couple you to all quantum fields simultaneously. You might spontaneously create and annihilate particles at an enormous rate, turning space around you into a seething cauldron of quantum activity. This could transform you from a simple traveler into a cosmic force that actively reshapes the quantum vacuum as you pass through it. The many worlds interpretation of quantum mechanics suggests that every quantum measurement creates multiple parallel universes, with each possible outcome occurring in a different branch of reality. At light speed, where quantum measurements might never occur due to infinite time dilation, you might gain access to all of these parallel worlds simultaneously. Instead of following a single path through the multiverse, you might exist in all possible parallel realities at once. Every decision you ever made, every quantum event that ever affected you, would create branches of reality that you could experience simultaneously. You would become a multiversal being, living all possible versions of your life in parallel. The quantum Zeno effect describes how frequent measurements can freeze the evolution of a quantum system, preventing it from changing states. At light speed, where time stops completely, this effect might become absolute. You might become frozen in a particular quantum state, unable to evolve or change in any way. This quantum freezing could preserve your consciousness in a specific configuration for all eternity. Conversely, the quantum anti-Zeno effect describes how certain types of measurements can accelerate quantum evolution. At light speed, this effect might allow you to experience accelerated quantum evolution, rapidly cycling through all possible quantum states. You might live entire lifetimes in instants, experiencing every possible version of yourself in rapid succession. The holographic principle in quantum mechanics suggests that all the information in a volume of space can be encoded on its boundary surface. At light speed, where spatial dimensions collapse, this principle might allow you to contain the information content of the entire universe. You would become a living hologram, encoding within yourself the complete description of cosmic reality. The emergence of classical reality from quantum foundations remains one of the deepest mysteries in physics. Through a process called decoherence, quantum superpositions typically evolve into classical, definite states when they interact with their environment. But at light speed, where environmental interactions might be suspended due to time dilation, decoherence might never occur. You might exist in a permanent state of quantum coherence, never collapsing into classical reality. This could preserve all quantum possibilities simultaneously, allowing you to exist as a living superposition of all possible states. You would transcend the boundary between quantum and classical reality, existing in both realms simultaneously. The concept of quantum consciousness, while speculative, suggests that consciousness itself might be a quantum phenomenon. If this is true, then light speed travel could fundamentally alter the nature of conscious experience. Your consciousness might become distributed across quantum fields, entangled with cosmic structures, and existing in superposition states that encompass all possible thoughts and experiences. The measurement problem in quantum mechanics asks how and why quantum superpositions collapse into definite states. At light speed, this problem might be resolved through the absence of time. Without time for interactions to occur, measurements might never happen, preserving quantum superpositions indefinitely. You might discover that the measurement problem only exists in classical space-time and disappears entirely in the timeless realm of light speed. Perhaps most profoundly, light speed travel might reveal that quantum mechanics and relativity are not separate theories, but aspects of a deeper unity. The quantum realm and the realm of space-time might merge at light speed, creating a unified description of reality that transcends both quantum mechanics and relativity. You would become an explorer not just of space and time, but of the fundamental quantum geometry that underlies all existence. In the quantum realm of light-speed travel, the familiar boundaries between self and universe, between possibility and actuality, between mind and matter, might dissolve entirely. You would enter a domain where consciousness, quantum fields, and space-time merge into a single unified phenomenon that encompasses all of reality in a timeless, boundless quantum symphony of existence. The way we perceive the universe is fundamentally shaped by our position within it and our speed of motion through space and time. From our earthbound perspective, moving at relatively slow speeds, we see a cosmos filled with discrete objects separated by vast distances, where events unfold in a logical sequence from past to future. But what would this familiar universe look like if you could observe it while traveling at the speed of light itself? How would your perception of reality change when you join the realm of photons and electromagnetic radiation? To understand how light-speed travel would transform your perception, we must first recognize that perception itself is a process that depends on the flow of information from the observed to the observer. Every act of seeing requires light to travel from objects to your eyes, where it is converted into electrical signals that your brain interprets as images. This process takes time, even if that time is usually imperceptibly short. But at light speed, this fundamental process of perception would be radically altered. One of the most dramatic changes would occur in your perception of time itself. From your perspective traveling at light speed, time would come to a complete stop. This means that you would not experience the passage of time in any conventional sense. There would be no sequence of moments, no progression from one instant to the next. Instead, you would exist in a single, eternal present that encompasses all of time simultaneously. This timeless perception would transform how you experience events in the universe. Instead of watching stars form and evolve over millions of years, you would witness their entire life cycle happening at once. The birth of a star from a collapsing gas cloud, its long period of nuclear burning, its eventual death as a supernova or white dwarf, all of these events would occur simultaneously in your timeless reference frame. The entire history of the universe would unfold before you as a single, static picture. Your perception of space would undergo equally profound transformations. Due to the length contraction effects of relativity, all distances in the direction of your motion would shrink to zero from your perspective. The familiar three-dimensional universe would collapse into a two-dimensional projection, with all points along your path of motion compressed into a single location. You would not see yourself moving through space, but rather existing simultaneously at every point in the universe that lies in your direction of travel. This spatial compression would fundamentally alter how you perceive the structure of the cosmos. Galaxies that normally appear separated by millions of light years would all occupy the same location from your perspective. The Milky Way, Andromeda, and the most distant observable galaxies would all appear to exist at the same point in space. The vast cosmic web of galaxy clusters and dark matter filaments would collapse into a single, infinitely thin structure. The electromagnetic radiation that carries visual information would also behave very differently at light speed. Due to the Doppler effect, light from objects ahead of you would be blue shifted to extremely high energies, while light from objects behind you would be red shifted to very low energies. This extreme Doppler shifting would completely change the appearance of the universe around you. Stars and galaxies ahead of you would disappear from visible light and appear instead as sources of intense gamma radiation. This high-energy radiation would be invisible to your biological eyes, assuming they could somehow function at light speed. The familiar starlight that illuminates our night sky would be transformed into a lethal beam of cosmic rays concentrated in the direction of your motion. Meanwhile, light from objects behind you would be red shifted into the radio spectrum and beyond. These objects would fade from view as their light was stretched to wavelengths too long for your eyes to detect. The universe behind you would become dark and silent, devoid of any electromagnetic signals that your senses could perceive. This creates a strange asymmetry in your perception of the universe. Ahead of you would be a blazing wall of high-energy radiation, while behind you would be an expanding realm of darkness. To either side, perpendicular to your motion, objects might appear at closer to their normal wavelengths, but even these would be affected by the relativistic beaming effects that concentrate radiation in the forward direction. The cosmic microwave background radiation, the faint afterglow of the Big Bang that pervades all of space, would also be dramatically transformed by your light-speed motion. This normally uniform radiation field would appear concentrated into an intense beam of gamma rays ahead of you. The temperature of this radiation, normally about 3 degrees above absolute zero, would appear to reach millions of degrees due to the blue shifting effect. Your perception of the cosmic microwave background would essentially turn the entire universe ahead of you into a blazing furnace of radiation. This wall of fire would be so intense that it would outshine all other sources of electromagnetic radiation, creating a universe that appears to be made entirely of concentrated Big Bang energy. But perhaps most remarkably, your perception at light speed might transcend the normal limitations of electromagnetic radiation altogether. If consciousness could somehow survive the transition to light speed, you might gain access to forms of perception that do not depend on the traditional senses. You might become directly aware of gravitational fields, quantum wave functions, or the geometric structure of space-time itself. This expanded perception could allow you to see the universe in ways that no biological creature has ever experienced. You might perceive the curvature of space-time around massive objects as directly as you now see colors. The quantum superposition states of particles might become as visible as the objects of everyday experience. The flow of information through quantum entanglement might appear as streams of connection linking distant parts of the cosmos. Your perception of matter itself would be transformed by light-speed travel. The atoms and molecules that make up ordinary objects would no longer appear as discrete, solid entities. Instead, you might perceive them as quantum clouds of probability, existing in superposition states that encompass all possible configurations simultaneously. The boundaries between different objects might blur or disappear entirely as you perceive the underlying quantum fields from which all matter emerges. The perception of causality would also be fundamentally altered. In normal experience, we see causes followed by their effects in a clear temporal sequence. But at light speed, where time stops and simultaneity breaks down, you might perceive all causes and effects as happening at once. The entire causal network that connects events throughout the universe might become visible as a static pattern, like a vast web spanning all of space and time. This could give you a godlike perspective on the universe, where you can see not just what is happening, but why it is happening, and how all events are interconnected. You might perceive the universe as a single unified structure, where every part affects every other part, through an intricate network of causal relationships that extend across space and time. Your perception of consciousness itself might be transformed at light speed. If consciousness is indeed tied to the flow of information through neural networks, then the stopping of time at light speed might freeze your conscious processes in their current state. Alternatively, you might experience a form of expanded consciousness that transcends the normal limitations of biological neural networks. This expanded consciousness might allow you to perceive not just your own thoughts and experiences, but the information processing occurring throughout the universe. You might become aware of the computational processes happening inside stars, the information storage and retrieval occurring in quantum systems, or even the data processing that underlies the evolution of cosmic structures. The boundary between self and universe might dissolve entirely at light speed. Your perception might expand to encompass not just your immediate surroundings, but the entire cosmos. You might experience yourself as existing simultaneously in every galaxy, every star system, and every planet in the universe. Your consciousness might merge with the fundamental information processing that drives the evolution of the cosmos. The concept of observation, so crucial to quantum mechanics, would take on new meaning at light speed. In the quantum realm, the act of observation causes wave functions to collapse and determines which of many possible realities becomes actual. At light speed, you might become a cosmic observer whose very perception shapes the reality of the entire universe. This power of cosmic observation might allow you to influence the fundamental structure of reality through the act of perception itself. By choosing what to observe and how to observe it, you might determine which quantum possibilities become actual throughout the cosmos. You would become not just a passive observer of the universe, but an active participant in its creation. The familiar concepts of here and there, now and then, would lose all meaning in your light speed perception. Instead of existing at a particular location and time, you might experience a form of omnipresence that encompasses all of space and time simultaneously. You would not be traveling through the universe, but rather existing as a fundamental aspect of the universe itself. Perhaps most profoundly, your perception at light speed might reveal that the universe is far more unified and interconnected than we realize from our limited earthbound perspective. The apparent separation between objects, the flow of time from past to future, the distinction between mind and matter, all of these might be revealed as illusions created by our slow motion through space-time. At light speed, you might perceive the universe as it truly is, a single, undivided whole, where all apparent separations are merely artifacts of limited perspective. Space, time, matter, energy, and consciousness might be revealed as different aspects of a single, unified reality that transcends all the categories we use to understand our everyday experience. In this ultimate perception, you would not see the universe differently. You would see that there is no difference between you and the universe at all. Observer and observed, perceiver and perceived, would merge into a single cosmic consciousness that encompasses all of reality in a timeless, boundless awareness that is both everything and nothing, everywhere and nowhere, eternal and instantaneous. While the physics we have explored so far suggests that light speed travel is impossible for objects with mass, the human imagination refuses to accept such limitations. Throughout history, theoretical physicists have proposed ingenious ways to circumvent the apparent impossibility of faster-than-light travel, developing mathematical models that might allow us to achieve what seems forbidden by the laws of nature. These theories push the boundaries of our understanding and offer tantalizing glimpses of what might be possible if we can master the deepest principles of space-time itself. One of the most famous theoretical approaches to faster-than-light travel is the concept of wormholes, first proposed by physicists in the early 20th century. A wormhole is essentially a tunnel through space-time that connects two distant regions of the universe. Instead of traveling through the normal three-dimensional space between 2 points, you could theoretically enter one end of a wormhole and emerge from the other end, having effectively traveled faster than light without ever exceeding light speed locally. The mathematics of wormholes emerges naturally from Einstein's equations of general relativity. These equations describe how matter and energy curve space-time, creating the gravitational effects we observe. Under certain exotic conditions, the equations allow for solutions where space-time curves back on itself, creating a bridge or tunnel that connects distant regions. The entrance and exit of such a tunnel are called the mouths of the wormhole. To understand how a wormhole might work, imagine space-time as a flat sheet of paper. Normally, to travel from one point on the paper to another distant point, you would have to move across the surface of the paper, covering the entire distance between the points. But if you could fold the paper so that the 2 points touch, you could poke a hole through both layers and create a shortcut that bypasses the normal surface distance. This is essentially what a wormhole does with the fabric of space-time itself. The theoretical advantage of wormhole travel is that you never actually exceed the speed of light in your local reference frame. As you pass through the wormhole, you are always moving slower than light speed, relative to the space-time immediately around you. The faster than light effect comes from the fact that the wormhole provides a shorter path through space-time than the conventional route through normal space. However, the physics of wormholes presents enormous challenges. For a wormhole to remain stable and traversable, it would require exotic matter with negative energy density. This exotic matter would need to possess repulsive gravitational properties, pushing space-time apart rather than pulling it together like normal matter. While quantum field theory suggests that such exotic matter might exist in principle, we have never observed it in nature, and it is unclear whether it can exist in the large quantities needed to maintain a macroscopic wormhole. Even if exotic matter could be obtained, the engineering challenges of creating and maintaining a wormhole would be staggering. The energy requirements might exceed the total energy output of entire galaxies. The precise control needed to shape space-time into a wormhole configuration would require technology far beyond anything we can currently imagine. Yet the theoretical possibility remains, tantalizingly suggesting that the universe might provide natural shortcuts for those clever enough to find and use them. Another fascinating theoretical approach is the Alcubierre warp drive, proposed by physicist Miguel Alcubierre in 1994. This concept involves warping space-time itself to create a bubble around a spacecraft. The space in front of the craft would be compressed while the space behind it would be expanded, creating a wave of distorted space-time that carries the ship along faster than light speed. The brilliant insight of the Alcubierre drive is that while space itself expands and contracts at rates faster than light, the spacecraft within the warp bubble never moves faster than light relative to its local space-time. The ship remains essentially stationary within its bubble, while space-time flows around it. This is similar to how a surfer rides a wave. The surfer is not moving faster than the water, but the wave carries the surfer forward at high speed. The mathematical description of the Alcubierre drive shows that it is consistent with Einstein's equations under certain conditions. The drive would create a region of flat space-time around the spacecraft, where the normal laws of physics apply, surrounded by regions of highly curved space-time that create the propulsive effect. Passengers inside the warp bubble would experience normal physics and could theoretically make the journey in comfort. However, like wormholes, the Alcubierre drive requires exotic matter with negative energy density to function. The amount of exotic matter needed would be enormous, possibly requiring the mass-energy equivalent of entire planets or stars. Recent refinements to the theory have reduced these energy requirements somewhat, but they remain far beyond our current technological capabilities. The Alcubierre drive also faces causality problems. If such a drive could be built, it might allow for time travel to the past, creating the familiar paradoxes we discussed earlier. The ability to send information or objects backward in time could lead to logical contradictions that might make the universe unstable or inconsistent. A third theoretical approach involves the manipulation of extra dimensions that might exist beyond the familiar 3 dimensions of space and 1 dimension of time. String theory and other advanced theoretical frameworks suggest that our universe might actually have 10 or 11 dimensions, with the extra dimensions curled up so small that we cannot normally detect them. If these extra dimensions could be accessed and manipulated, they might provide shortcuts that allow faster than light travel. The concept of extra-dimensional shortcuts is based on the idea that what appears to be a vast distance in our familiar three-dimensional space might correspond to a much shorter distance when measured through higher dimensional space. By traveling through these extra dimensions, you might be able to reach distant locations much more quickly than would be possible through normal three-dimensional space. Some theories suggest that certain fundamental particles, such as gravitons that carry the gravitational force, might already have access to these extra dimensions. This could explain why gravity is so much weaker than the other fundamental forces. Its effect might be diluted by spreading into the extra dimensions. If we could learn to follow the same paths that gravitons take through higher dimensional space, we might achieve forms of travel that transcend the normal limitations of space-time. The manipulation of extra dimensions would require understanding and controlling physics at energy scales far beyond what we can currently achieve. The extra dimensions might only become accessible at energies comparable to those present in the first moments after the Big Bang. Creating such conditions artificially would require particle accelerators millions of times more powerful than anything we have today. Quantum mechanical approaches to faster-than-light travel focus on the strange properties of quantum entanglement and quantum tunneling. As we discussed earlier, quantum entangled particles can influence each other instantaneously across arbitrary distances. While this cannot be used to transmit information faster than light under normal circumstances, some theorists have speculated about ways to harness quantum entanglement for communication or even transportation. One proposed approach involves creating macroscopic quantum entanglement between distant locations. If large-scale objects could be quantum entangled, it might be possible to teleport matter or information from one location to another without the intervening journey. This would essentially be a form of quantum teleportation, scaled up from individual particles to macroscopic objects. The challenges of macroscopic quantum entanglement are immense. Quantum entanglement is extremely fragile and is easily destroyed by interactions with the environment. Maintaining entanglement for large objects over long distances and time periods would require isolating the entangled system from all external influences, a task that becomes increasingly difficult as the size and complexity of the system grows. Quantum tunneling offers another potential approach to faster-than-light travel. In the quantum world, particles can tunnel through barriers that should be impenetrable according to classical physics. Some theories suggest that under certain conditions, this tunneling effect might allow particles or even larger objects to traverse distances faster than light. The key insight is that quantum tunneling is not limited by the normal speed restrictions of classical motion. When a particle tunnels through a barrier, it does not follow a continuous path through space, but rather disappears from one side of the barrier and reappears on the other side. The time required for this process might be independent of the barrier width, potentially allowing faster than light traversal of large distances. However, scaling quantum tunneling up to macroscopic objects faces the same challenges as macroscopic entanglement. The quantum effects that allow tunneling become increasingly unlikely as objects become larger and more complex. The probability of a human being spontaneously tunneling through even a thin wall is so vanishingly small that it would never occur in the lifetime of the universe. Some of the most speculative approaches to faster-than-light travel involve manipulating the fundamental constants of nature or exploiting hypothetical modifications to the laws of physics. These theories suggest that what we consider to be fixed laws might actually be variable under certain extreme conditions. For example, some theories propose that the speed of light itself might not be truly constant but could vary under different circumstances. If the speed of light could be increased in a local region of space-time, objects within that region might be able to travel faster than the normal light speed limit without violating causality. Alternatively, if the speed of light could be decreased everywhere except in a chosen path, that path might provide a faster route through space-time. The manipulation of fundamental constants would require understanding physics at a level far deeper than our current theories provide. It might involve accessing the quantum structure of space-time itself or manipulating the fields that give rise to the fundamental forces. Such capabilities would represent a mastery of nature so complete that faster-than-light travel might be just one of many miraculous achievements. Another speculative approach involves the creation of closed time-like curves, paths through space-time, that loop back on themselves in time. While these would not provide faster-than-light travel in the conventional sense, they could allow you to arrive at your destination before you left, effectively achieving the same result as instantaneous travel. Closed time-like curves arise naturally in certain solutions to Einstein's equations, particularly those involving rotating black holes or cosmic strings. However, these solutions typically require exotic conditions that may not exist in our universe, and they raise serious causality problems that could threaten the logical consistency of space-time. The theoretical models we have explored represent some of the most creative and ambitious attempts to overcome the apparent impossibility of faster-than-light travel. While none of these approaches have been experimentally verified, and many face seemingly insurmountable theoretical and practical obstacles, they demonstrate the power of human imagination and mathematical reasoning to explore possibilities beyond our current understanding. Perhaps most importantly, these theoretical models reveal that the question of faster-than-light travel is not simply a matter of building better rockets or more powerful engines. It is fundamentally a question about the nature of space-time itself, about the relationship between matter and geometry, and about the deepest principles that govern the structure of reality. Whether any of these theoretical approaches will ever lead to practical faster-than-light travel remains an open question. The challenges are enormous, and the energy requirements are staggering. But the history of science is filled with achievements that once seemed impossible, and the theoretical foundations for faster-than-light travel, while speculative, are rooted in our best current understanding of physics. As we continue to push the boundaries of our knowledge and develop new technologies, we may discover that the universe provides pathways to faster-than-light travel that we have not yet imagined. The cosmos may hold secrets that will one day allow us to transcend the apparent limitations of space-time and achieve the dream of traveling at the speed of light itself. Imagine a future where humanity has somehow overcome the seemingly impossible barriers to light-speed travel. Picture a time when the theoretical models we explored have been transformed into working technologies, when the vast distances that currently separate us from the stars have been reduced to mere steps in a cosmic journey. How would such a breakthrough transform not just space exploration, but the very nature of human civilization and our understanding of the universe itself? The advent of light-speed travel would represent the most profound revolution in human history, dwarfing even the agricultural revolution, the industrial revolution, and the information revolution in its scope and impact. It would fundamentally alter our relationship with space, time, and the cosmos, opening possibilities that we can barely imagine from our current earthbound perspective. The most immediate impact would be on space exploration itself. Currently, our robotic missions to the outer planets of our solar system take years or decades to reach their destinations. The Voyager spacecraft, launched in 1977, are still traveling through space nearly 5 decades later, having only recently reached the edge of our solar system. A mission to the nearest star would take tens of thousands of years with current technology, making interstellar exploration effectively impossible within human lifespans. Light-speed travel would compress these vast timescales into manageable intervals. A journey to Mars, which currently takes 6 to 9 months, could be completed in minutes. A voyage to the outer planets could be accomplished in hours. Most remarkably, travel to the nearest star systems could be achieved in years rather than millennia, bringing interstellar exploration within the realm of practical possibility. But the true revolution would extend far beyond reduced travel times. Lightspeed travel would make the entire galaxy accessible to human exploration and colonization. The Milky Way, with its 400 billion stars and countless planetary systems, would become humanity's neighborhood, rather than an unreachably distant realm. We could send expeditions to investigate potentially habitable worlds, establish colonies around distant stars, and begin the greatest migration in human history. This galactic expansion would have profound implications for human civilization. Instead of being confined to a single world orbiting a single star, humanity could spread across thousands or millions of star systems. This distribution would provide unprecedented security for our species, making us essentially immune to the kinds of catastrophic events that could threaten all life on a single planet. Asteroid impacts, supervolcanic eruptions, or even the eventual death of our sun would no longer pose existential threats to human civilization. The establishment of interstellar colonies would also drive unprecedented scientific and technological advancement. Each new world would present unique challenges and opportunities, forcing us to develop new technologies and adapt to alien environments. The diversity of conditions across different star systems would accelerate innovation at a pace that would be impossible if we remained confined to Earth. Moreover, light-speed travel would enable real-time communication across interstellar distances from the perspective of the travelers. While messages between star systems would still be limited by light speed for stationary observers, travelers moving at light speed could potentially maintain instantaneous contact with their destinations. This could create a galaxy-spanning communication network that keeps human civilization connected across vast distances. The discovery and study of extraterrestrial life would be revolutionized by light-speed travel. Currently, our search for life beyond Earth is limited to remote observations and the analysis of signals that may have traveled for years or decades to reach us. With light-speed travel, we could directly visit potentially habitable worlds and conduct detailed investigations of any life forms we discover. The implications of finding life elsewhere in the galaxy would be staggering. Each new biosphere would provide insights into the fundamental principles of life and evolution. We might discover entirely new forms of biochemistry, new evolutionary strategies, or even new types of consciousness. The study of alien ecosystems could revolutionize our understanding of biology, ecology, and the potential for life in the universe. If we encounter intelligent alien civilizations, light-speed travel would enable direct contact and communication. Rather than waiting decades or centuries for radio signals to traverse interstellar space, we could visit other civilizations and engage in face-to-face diplomacy, cultural exchange, and scientific collaboration. This could lead to a galactic community of intelligent species sharing knowledge and resources across the stars. The economic implications of light-speed travel would be equally transformative. The resources of entire star systems would become accessible, effectively providing unlimited raw materials for human civilization. Asteroid mining, which is already being considered for our solar system, could be extended to the asteroid belts and planetary systems of countless other stars. More exotic resources might also become available. Neutron stars, for example, contain matter compressed to densities unimaginable on Earth. White dwarf stars might provide access to exotic forms of matter that exhibit unusual properties. Gas giants around other stars might harbor atmospheric compositions that could yield valuable materials not found in our solar system. The energy resources of the galaxy would also become accessible through light-speed travel. We could harvest the energy output of multiple stars, tap into the rotational energy of black holes, or exploit other high-energy phenomena that exist throughout the galaxy. This could provide energy resources on scales that would make our current energy needs seem trivial. Light-speed travel might also enable forms of exploration that transcend our local galaxy. The nearest major galaxy, Andromeda, lies over 2.5 million light-years away. While this distance would still require millions of years of travel time from an external perspective, it would be traversed instantaneously from the traveler's point of view. This could make intergalactic exploration possible, opening up hundreds of billions of other galaxies for investigation. The scientific discoveries that would result from galactic and intergalactic exploration are almost impossible to predict. We might find evidence of previous galactic civilizations that have risen and fallen over cosmic timescales. We could discover new physical phenomena that only occur under the extreme conditions found in different parts of the galaxy. We might even find clues about the ultimate fate of the universe, or the existence of other universes beyond our own. The development of light-speed travel technology would itself drive massive advances in our understanding of fundamental physics. The engineering required to manipulate space-time, harness exotic matter, or access extra dimensions would necessitate breakthroughs in theoretical physics, materials science, and energy production. These advances would likely have applications far beyond space travel, potentially revolutionizing every aspect of human technology. The social and philosophical implications of light-speed travel would be equally profound. The ability to explore the galaxy would fundamentally change humanity's perspective on our place in the universe. We would transition from being the inhabitants of a single world to being citizens of the galaxy itself. This expanded perspective might lead to new forms of philosophy, art, and spirituality that reflect our cosmic citizenship. The relationship between different human populations would also be transformed. Currently, the isolation imposed by vast distances helps maintain cultural diversity among different human societies. With light-speed travel, this isolation would be broken down, potentially leading to a more unified human civilization. Alternatively, the settlement of different star systems might lead to new forms of cultural diversification as human populations adapt to alien environments. The governance of a galactic human civilization would present unprecedented challenges. How would democracy function across interstellar distances? How would laws be enforced in star systems that are light years apart? How would resources be distributed fairly among colonies that may have vastly different capabilities and needs? These questions would require entirely new forms of political and social organization. Light-speed travel might also enable new forms of art and entertainment that exploit the unique properties of relativistic motion. Artists could create works that exist across multiple star systems simultaneously, or that evolve over cosmic timescales. Musicians could compose symphonies that resonate with the natural frequencies of different astronomical objects. The possibilities for creative expression would be expanded beyond anything we can currently imagine. The preservation of knowledge and culture would take on new importance in a galactic civilization. With human populations spread across thousands of star systems, the loss of any single colony would represent the potential disappearance of unique cultural developments and scientific discoveries. This might drive the development of sophisticated systems for backing up and preserving human knowledge across multiple locations. Education would also be transformed by light-speed travel. Students could visit other star systems as part of their studies, gaining first-hand experience of alien environments and phenomena. The ultimate field trip might involve visiting black holes, neutron stars, or other exotic astronomical objects to observe physics that cannot be replicated on Earth. Perhaps most profoundly, light-speed travel might reveal that our current understanding of the universe is fundamentally incomplete. The ability to explore cosmic phenomena directly, rather than relying on remote observations, could uncover new physics that revolutionizes our understanding of reality. We might discover that the universe is far stranger and more wonderful than we currently imagine. The development of light-speed travel could also mark the beginning of humanity's transition to a post-biological civilization. The extreme conditions involved in light-speed travel might require abandoning biological bodies in favor of artificial forms that can better withstand the stresses involved. This could lead to new forms of consciousness and identity that transcend the limitations of biological existence. In the ultimate scenario, light-speed travel might enable humanity to explore not just our universe, but other universes as well. If the theoretical frameworks that suggest the existence of multiple universes or extra dimensions prove correct, light-speed travel might provide access to realms of existence that are completely alien to our current experience. The future of space exploration enabled by light-speed travel would transform humanity from a planetary species to a cosmic force. We would become explorers of the infinite, citizens of the galaxy, and ultimately participants in the grandest adventure imaginable, the complete exploration and understanding of all reality. The universe would no longer be a distant and unreachable realm, but our home, our laboratory, and our destiny. In this future, the question would not be whether we can reach the stars, but how quickly we can explore all of them. The cosmos would become not just our destination, but our domain, and the light-speed travel would be the key that unlocks infinite possibilities for growth, discovery, and transformation. The universe awaits, vast and wonderful, ready to reveal its secrets to those bold enough to travel at the speed of light itself. As our journey through the mysteries of light-speed travel draws to a close, we find ourselves contemplating questions that stretch far beyond the boundaries of current human knowledge. We have explored the deepest principles of physics, ventured into realms where time stops and space collapses, and imagined futures where humanity transcends its earthbound limitations to become citizens of the cosmos itself. Yet perhaps the most profound realization is that we have only begun to scratch the surface of the infinite mysteries that surround us. The speed of light represents more than just a velocity. It is a fundamental constant that weaves together the very fabric of reality. In our exploration, we have seen how this seemingly simple number connects space and time, matter and energy, quantum mechanics and relativity, consciousness and cosmos. Light speed is not merely fast, it is the pace at which the universe itself unfolds, the rhythm that underlies all existence. Through our investigation of what it would mean to travel at light speed, we have glimpsed the extraordinary nature of the reality we inhabit. We have discovered that time is not the steady river we once thought, but a flexible dimension that can be stretched and compressed. We have learned that space is not the fixed stage of our existence, but a dynamic fabric that can be curved and folded. We have seen that the boundaries between observer and observed, between mind and matter, between self and universe, may be far more fluid than our everyday experience suggests. The paradoxes we encountered along the way serve as reminders that the universe is under no obligation to conform to our intuitions or expectations. Reality, at its deepest levels, operates according to principles that challenge our most basic assumptions about existence. Yet these same paradoxes point toward truths that are more beautiful and profound than anything we might have imagined. The apparent impossibilities of light-speed travel reveal not the limitations of nature, but the richness and complexity of the cosmos we inhabit. The physical challenges of light-speed travel, from infinite energy requirements to the breakdown of biological processes, remind us of the extraordinary conditions that would be required to achieve such motion. Yet these same challenges inspire us to think beyond the constraints of our current understanding, and to imagine forms of existence that transcend our biological limitations. Perhaps the journey toward light speed is not about moving our current forms faster, but about transforming into something capable of joining the timeless dance of photons. The quantum realm revealed through our exploration adds layers of mystery and possibility that extend far beyond classical physics. In the quantum world of light-speed travel, consciousness might expand to cosmic proportions. Reality might exist in permanent superposition, and the very boundaries of existence might dissolve into a unified field of pure possibility. These quantum mysteries suggest that light-speed travel might be less about transportation and more about transformation, into fundamentally new modes of being. The theoretical models we examined, from wormholes to warp drives, demonstrate the power of human imagination to transcend apparent limitations through mathematical insight and creative thinking. While these approaches face enormous challenges, they remind us that the history of science is filled with achievements that once seemed impossible. The technologies that might one day enable light-speed travel may emerge from entirely unexpected directions, perhaps requiring insights that we cannot yet imagine. The future we envisioned, where light-speed travel transforms human civilization into a galactic community, represents both an inspiring possibility and a profound responsibility. The power to traverse the cosmos at light speed would come with the obligation to use such capabilities wisely, to explore with respect and humility, and to recognize our role as temporary stewards of cosmic possibilities that extend far beyond our individual existence. But perhaps the most important insight from our journey is that the question of light-speed travel ultimately leads us back to fundamental questions about the nature of existence itself. What does it mean to be conscious in a universe where time and space are relative? What is the relationship between mind and cosmos? Are we separate observers of reality or integral participants in its ongoing creation? These questions persist, whether we ever achieve light-speed travel or not, and they remind us that the deepest explorations are often inward journeys into the mystery of consciousness itself. As we rest beneath the countless stars that illuminate the night sky, we can appreciate the remarkable fact that the light entering our eyes has journeyed across vast distances at the speed we have been contemplating. Each photon carries information from distant suns, having traveled for years, or decades, or centuries to reach us in this moment. In a very real sense, we are already participants in light-speed travel, receiving messages from across the cosmos through the gentle medium of starlight. The photons that allow us to see the universe have experienced no passage of time during their journeys to us. From their perspective, they were emitted and absorbed in the same instant, even though years may have passed in our reference frame. This means that every time we look at the stars, we are connecting with a timeless realm that transcends the normal flow of temporal experience. We are already in contact with the light-speed domain that we have been exploring. This connection to the timeless realm of light suggests that the boundaries between our everyday experience and the exotic physics of light-speed travel may not be as absolute as they first appear. Through observation, through contemplation, through the simple act of looking up at the night sky, we participate in processes that connect us to the deepest mysteries of space and time. We may not be able to travel at light speed with our physical bodies, but our awareness can touch the timeless realm where light exists. The endless possibilities of time and space extend in all directions from this moment of quiet contemplation. Behind us lies a cosmic history stretching back over 13 billion years to the Big Bang itself. Ahead of us lies a future that may extend for trillions of years, encompassing the birth and death of countless stars and the ultimate fate of the universe itself. Above us stretch galaxies containing hundreds of billions of stars, each potentially hosting worlds where other forms of consciousness may be pondering the same mysteries we contemplate. In this vast cosmic context, our exploration of light-speed travel becomes more than a scientific investigation. It becomes a meditation on our place in the infinite tapestry of existence. We are not merely observers of the universe, but expressions of the universe's capacity for self-awareness. Through our consciousness, the cosmos contemplates itself, wonders about its own nature, and dreams of traveling at the speed of light. And the journey we have taken together through the mysteries of light-speed travel may end here, but the deeper journey of cosmic exploration continues with every breath, every heartbeat, every moment of conscious awareness. We are already traveling through space-time at remarkable speeds, carried along by Earth's rotation, orbital motion, and the movement of our solar system through the galaxy. We are already participants in the cosmic dance, already connected to the infinite web of space and time that encompasses all existence. As we close our eyes and allow the gentle rhythm of breathing to carry us toward rest, we can carry with us the wonder and mystery we have explored. In sleep, consciousness takes its own journey through realms that may be no less mysterious than the light-speed domain we have investigated. Dreams may provide their own form of faster-than-light travel, connecting us to possibilities that transcend the normal limitations of space and time. The universe continues its ancient dance while we sleep, stars continuing to shine across impossible distances, galaxies slowly rotating through cosmic time, light carrying information between distant worlds at the speed that defines the structure of reality itself. We rest as participants in this cosmic symphony, temporary expressions of the universe's infinite creativity and endless capacity for wonder. Tomorrow will bring new questions, new discoveries, new opportunities to explore the mysteries that surround us. The speed of light will continue to define the boundaries of the possible, to connect space and time in ways that challenge our understanding, and to remind us that reality is far stranger and more beautiful than we can fully comprehend. But tonight, we rest in the knowledge that we have touched something profound, something that connects us to the deepest truths about existence itself. The endless possibilities of time and space await, infinite and eternal, ready to reveal new wonders to minds curious enough to ask the deepest questions and hearts open enough to embrace the mystery. The universe is vast beyond imagination, yet it is also intimately present in this moment of awareness, this breath, this heartbeat, this consciousness that contemplates the speed of light and dreams of traveling among the stars. In the end, perhaps the greatest journey of all is not the one that takes us to distant galaxies at impossible speeds, but the one that brings us home to the miracle of conscious existence in a universe capable of contemplating itself. Light-speed travel may remain forever beyond our reach, but the light-speed realm is always available to awareness, always present in the timeless moment where all possibilities converge, always ready to welcome us home to the infinite mystery of being.